Hey there, pre-calculus fans. We're going to do part 3 here. We're going to do an example which I would encourage you to try on your own. I'm going to do it first with the graphical approach, what I just presented in part 2. And this is my intention in class. And then I was going to do it again with the algebraic approach. I don't know if that's a good name for it, but with an approach where I just mechanically use this idea of adding pi at the right time with the right sign. As I said in the previous video, I'm a proponent, I think, in the long run for having the graphical idea, but I want to give you everything you can get in case you prefer this other way. All right, so anyways, we're going to use, I just chose signs so that it would be simpler. In the situation where you're just dealing with sign, the algebraic method probably makes a lot of sense, and since that happens quite a bit, it's worth bringing that in. But let's go. So remember, step 1, we find the principal solution. Our calculator tells us that. For this problem, I want everything in radians. Again, assume that unless otherwise stated. So we type that in our calculator. Let me grab my calculator, bring it in. So we are going to do I'm in radians. I'm going to do inverse sine of 0.6. Success. 0.64. And I'm doing this on the fly. Sometimes I say to my students, why doesn't he prepare? During lecture, I often have my notes sitting there, and I'm like, what is this? And I forget they're there. Okay, so anyways, that's our principal solution. Step 2, we draw the picture. Now, I know what sine looks like. This particular one is just the normal sine that goes up and down and up, starts at 0, repeats every 2 pi. If you do this enough, you get to where you maybe don't even need to graph it, but having the picture in your head is really helpful. So that's what I have now. So I already can I know it repeats every 2 pi. So if I sort of skip, I'm going to use symmetry, and then I will be done. At the end of the problem, one of my family of solutions will be 0.6435 plus 2 pi times k, where k is an integer. And that will give me all of these solutions here. So I like to say to students, that doesn't take very long. So if you sort of step back from whatever your confusion is, we can find the principal solution and the entire family that comes with it in a matter of moments. So if you sort of have that in mind, then you realize there's just one task, which is to find the symmetric solution. Now that right there is at pi over 2. How do I know that? It's a fourth of a period. That's its own thing. But I know the idea. I'm going to do pi over 2 minus the answer we just got. Whatever I get then, I'm going to add that to pi over 2. That's how I remember it. Now there's little shortcuts I could give you, but I like to give you the way that I remember it in my hopes that you can remember it too. So anyways, that's the answer I have in there, 0.6435. And so I need to do pi over 2 minus that. So I'm going to type pi divided by 2 minus that answer we just had. Done. So this is, that little gap between them is 0.927295. I'm going to put that here and add it on. So you really just do plus pi over 2. Enter. And I'm getting this messy number, 2.498 in change, 0.91. That's the other family of solutions. Let's just round to 4. Problem would tell you where k is an integer. Let's be fancy. This actually means k is an integer. Oh, I shouldn't do that. You can just say it in words. K is an integer. Hooray! And we have all the solutions. Well, as always, you could test them. I mean, at any point, this is always good when you're solving. You could do sine of 2.4981. Really close to 0.6. It's not, because I rounded, it's not going to be. Okay. That's it. So I did want to compare that with this table. So I find it easier to remember the graph idea than the table idea. in my experience, instead of working with students. But the table idea says, hey, there's a certain thing that happened right here. And the thing that happened here, if you sort of think about it carefully, is you did pi over 2 minus whatever solution you got here. Maybe I'll do x sub p for principal. And you got a number. And then you added that on to pi over 2. So if you take this and add it on to pi over 2, what do you get? Well, you get pi minus the principal solution. Aha! So that actually gives us a direct way to solve it. What I mean by that is when you have sine of x equals 0.6, and you know you're in that exact situation where you're working just with sine, there are two solutions. This is kind of like using plus or minus when you're doing square roots. The two solutions we can explicitly give that are closest to where we started are the principal solution and the symmetric solution. But in the case of just sine by itself, the symmetric solution is pi minus whatever this was. So the idea is you can then just say those are your two answers. So you just need to do pi minus your principal. The downside of that is this is only for if you have sine by itself. And so when you're using this in some other problem, you have to identify when is sine by itself and then keep track of that throughout. Okay, so in this case, this is way faster because it's sine by itself. So the two answers are arc sine of 0.6 plus 2 pi k, which is this answer. And the other answer is pi minus arc sine. So in my experience, when students start using this, they go, oh yeah, all I need to do is pi minus and I have it. So that's when I would flip back to the problem I just did in my previous video and have students think, now where would you do the pi minus? And so this is what my worry about this method is if you do pi minus, you're not going to get that. It's not at the end. So then we have this challenge of when do we do it? Do we do it at the beginning? And the key moment when you would do it is right here, when you use the inverse sine. But then you still have more solving to do. So if you wanted to use this method, you absolutely can. This is just born out of experience of doing these problems with students that they tend to get this part wrong, but you would do two possibilities. So in addition to the one we have written here, you would write the following. You would write this plus 2 pi k. That's one family of solutions. And then you would solve keeping the 2 pi k throughout the rest of the solving. That would give you one collection of solutions. And if you did, you would eventually get here. The other collection of solutions, you would do this. You would say equals pi minus inverse sine of 1/3 plus 2 pi k. And then you would do the same thing. Then you would keep solving, and that would be this solution. So it adds this issue that the k appears earlier in your solving, and you have to keep track of it. It also adds this issue that you have to do it at the right moment. It's not really that bad either, but you would need to know that the moment you do the inverse sine, you would then write the full general solution from the table here. So the challenge of this method is that you would use this information the moment you hit the inverse sine button. And you would have to write this general solution and then keep solving from there. Okay, so this would mean that in the step before this, you would have, and there's a full another example in the textbook, which is always a good place to look. The very next step you would write after this would be this, and this, and then you would keep solving based off of whatever is in place of theta. Okay, so that's the algebraic method for comparison. As I said, I know both, I can do both, but I've just over the years seen fewer mistakes with, I've I've seen mistakes with both, but fewer mistakes with the idea method. And I would argue that you do this, it's rare enough. If you're going to solve lots of inverse trig, then it'd be good to know the algebraic, I think. But if you're just going to occasionally do an inverse trig, if you're just finding the principal solution, you don't have to remember the graph. But if you want to find the second or third solution, to me, it's always just easier to say, okay, where's the symmetry in the problem? So that's the philosophy. But our textbook goes through both, and I'm not biased against one or the other. I just was suggesting what I think will lead to fewer errors and also give you good practice with your graphing. All right, hope that sort of helps.